The methods for solving systems of nonlinear equations, like this one, right? The second equation in particular is nonlinear. It's got that exponent in it. The methods that we use here are the same as the ones we use for the linear cases, right? We're going to use the substitution method. We're going to use the elimination method. And so the methods are going to be familiar, but there are some additional considerations you've got to be concerned with. And I've picked some questions here that'll help to illustrate those. So both of these equations already conveniently solve for y. So I'm going to use the substitution method here. And I'm going to replace the y in the second equation with x plus 2. Right? It becomes x plus 2 equals x squared minus 4. Now I've got a polynomial equation, which I know how to solve. I'll set it equal to 0, subtract x from both sides, and subtract 2 from both sides. This becomes x squared minus x minus 6 equals 0. And this factors. It's x minus 3 times x plus 2. And we get two answers here. The x minus 3 factor gives us 3. And the x plus 2 factor gives us negative 2. And of course, now we're not done. Right? We still need to find the corresponding y value. Now, which one you substitute back into shouldn't matter. Right? You should get the same answers either way. So I usually try to pick the one that looks the simplest. Right, so I'm going to put them into that y equals x plus 2 equation. So if I put 3 in there, I get y equals 5. So my first solution is 3 comma 5. And if I put negative 2 in here, I get 0. So my second solution is negative 2 comma 0. Right, and there we go. There's our answers. Now, the reason I put a grid over here for us to work with these nonlinear equations, it's often helpful when you can to graph the equations. Because as you can see here, right, unlike what we've seen in the previous linear examples, here we've got two solutions rather than one. Graphing can often help you to really kind of see how many solutions you should have. Right, so y equals x plus 2, that's just a line. It's got a y-intercept of 2 and a slope of 1, so it's going to look something like this. And y equals x squared minus 4 is a parabola. If we factor that, it's x plus 2 times x minus 2. So the y-intercepts are negative 2 and 2, and that's good, right? Because that spot right there, negative 2 comma 0, that was one of our two solutions. That's good. And what else do we know? It opens up, and its y-intercept is negative 4, so it's going to be down here. All right, so it's going to have that kind of standard parabolic shape. Looks like this. And it's going to come up over here. You can see this is confirming, right? We should have two solutions. We're going to have the one here that we already noticed, and we've got another one here. And look, I swear I wasn't trying to aim for a perfect match, but you can see if we go over 3, up 1, 2, 3, 4, 5, yeah, that's really close. My graph is confirming not only the number of solutions, but it's really kind of making me confident about the numeric values as well. So we've got a second example here for us to look at. And the equations are both already solved for y. So I'm going to do this using the substitution method again. I'm going to put the square root of x plus 5 equals x minus 1, and then square both sides. X plus 5 equals x minus 1 squared. So x plus 5 equals x squared minus 2x plus 1. And I've got a polynomial equation, so I'll set this equal to 0, subtract x from both sides, and subtract 5. This becomes x squared minus 3x minus 4 equals 0. And this is nice, it factors. This is x minus 4 times x plus 1 equals 0. So I'm getting two answers. X minus 4 gives me 4, and x plus 1 gives me -1. Okay, good. So now I have to go back and find the y values, right? So if I put these into the, I'll use the second equation, right? When x equals 4, y is 4 minus 1, that's 3. So there's my first point, 4 comma 3. And when x is -1, I get my second point, right? Y equals -1 minus 1, which is -2. So I get two answers here. All right, now here's why I picked this one. When you're solving these systems of linear equations, of nonlinear equations, you have to check your answers, right? You absolutely have to, right? Because watch what's going to happen. When I check 4 comma 3, I don't need to check them in the second equation. I know they work in that one. It's the one I used to find them in the first place. It's the other one I need to check these in. So when I check it in there, this is the square root of 4 plus 5. That's the square root of 9, which is 3. Good. That one's fine. Let's try the other one. Let's put -1 in here. The point is -1, -2. This gives me y equals the square root of -1 plus 5. That's the square root of 4, which is +2, not -2. Right, so we have an extraneous solution here, and my only solution ultimately is 4 comma 3. All right, so what happened? Well, let's take a look. Let's take a look at the graphs. Y equals x minus 1 is a line. The y-intercept is down here at -1. So this is going to look something like this. Now this other one, y equals the square root of x plus 5, that is just a standard square root graph, right? You know what that looks like. It's got this shape. Shifted 5 units to the left, right? So if I go 1, 2, 3, 4, 5, put -5 in there, yeah, you get 0. Okay, good, right? That's what we expected. And then what happens? Then, I mean, it follows that shape, right? And this is, in fact, I did take aim that time, I'll admit, right? This is a relatively flat, slow-growing line. So you see what happens now, right? Because it doesn't have this lower half down here. It's this lower half that would have intersected here at a -x value, right? But because the square root function it only takes on positive values, we in fact only have that one solution, right? So the takeaway here, right? First, you can see again how the graph really helps tell us what's going on. The graph really is confirming that I should only have one solution here. But you need to go back and check your work to see if you ran into one of these kinds of extraneous solution situations. So I've got one more example for us to look at here. Now, the ones we've done so far have all used the substitution method. And in my experience teaching this, at least in a teaching setting, the substitution method is most often the one you kind of end up using. This one, however, is kind of set up for the substitution method. First, I'm really not particularly excited about trying to solve these for one of the variables because it's likely there's going to be square roots and plus or minuses involved, and that's a mess. So I see here I've got an x squared and an x squared, and those are my only x's. So this is why the elimination method often doesn't work. If there had been an x here, for example, yeah, okay, now eliminating the x's is going to be hard because there's no x in the bottom equation. It turns into kind of a mess. But because there's only x squareds in each one, that's the method I'm going to go for. So first, I'm going to take this one, and I'm going to kind of do the obvious. I'm going to move that 4 over. I'm going to make this 4y squared minus x squared equals -4. And then I'm going to multiply it by 2. And I'm going to write that down here under the other one. So this will be 8y squared minus 2x squared equals negative 8. And if I add these together, now you see, got the elimination method going. The x squares cancel. 11y squared equals negative 2. And I'm going to stop right there. I can see already I'm in trouble. Right? I've got a y squared is the only variable on the left side, and the right side is a negative number. Right? So if you don't see, you can carry it a little further. Divide by 11. Y squared equals negative 2/11. And now you try to take the square root of both sides, you're in trouble, because you can't take the square root of a negative number. All right? At this point, I'm just limiting the discussion to real valued solutions. If you're okay with imaginary solutions, yeah, okay, you can keep going from here. All right, so what does that mean? Well, there's no y values that work, so we've seen this before. This is another no solution scenario, right? In the past, our no solutions, we've seen that it was going to be no solutions for the answer when we got a false statement, like 0 equals 3, for example. And that really is what's happened here. We have gotten a false statement. There is no way the square of a number, square of a real number, equals negative 2/11. All right, so visually, what's going on here? Well, this curve here is a hyperbola, right? Specifically, it's a hyperbola, and you got to be careful now because of this negative over here, right? If I make that positive by multiplying through by negative 1, this will be x squared minus 4y squared equals positive 4. Then divide both sides by 4. We get x squared over 4 minus y squared equals 1. And now it really looks like the standard form of the equation of a hyperbola. So what does it look? Well, I'm not going to get super specific about my graph. Suffice it to say that it's a hyperbola and it opens left to right. Right, so it's going to look something like this. You got to work with me. We talked about this before. My art skills are really sketchy. Okay, so something like this. And what's the other one? Well, that 3y squared plus 2x squared, that's an ellipse, right? And if we divide through by 6, this becomes y squared over 2 plus x squared over 3 equals 1. So the major and minor axes are relatively small. Right, we're going to the square root of 4 and the square root of 3. Square root of 4 is 1.1. Square root of 3 is 1.7. Right, so what's happening here is we have an ellipse, and it's centered at the origin, and it looks something like, oh, that's really bad. Sorry, that was really bad even for me. Have to try that again. There we go. And looks, oh, that's not a whole lot better. But you get the idea. It looks something like this. We have this hyperbola, and we have an ellipse that is kind of squished in between the two branches. Right? So, yeah. And in that scenario, the graphs don't cross, and we end up with no solution. So again, the graph is helpful in that it helps us to confirm that our conclusions from the algebraic solution do make sense.